Right. So last time we were discussing about the computation part, and today we are going to look at the second very important part of the CUDA parallel processing, and that is related to memory. As you know that GPUs are suitable for data parallel operations. So when it comes to computation part, yes, you get large amount of performance and so on. But for some codes, it works out fine. For some other codes, it turns out that somehow, irrespective of how many threads you launch, somehow you don't get that much performance, as much as you would expect. And there are multiple reasons behind them, and one of them is going to be dealing with memory. And therefore, it's very important that we look at how you understand what kind of memory you are using, plus how to optimize your program for CUDA to take advantage of some of the different kinds of memories that it supports. Right. So let's learn that in today's class. The overall memory model of CUDA involves different kinds of memories. Right. So let's focus on the diagram first. We have this host, which is shown to be small, but it's a big beast, which is our CPU. And then this right-hand side portion is essentially your GPU, which is running one grid. Right? So one grid meaning it's running one kernel at a time. It's possible that multiple kernels can be run simultaneously on a GPU, but for now we'll say that there is one kernel running. The kernel, as we said, is going to be decomposed into multiple blocks, and each block, right? So each block has something called as a shared memory associated with it. Right? This shared memory is, as you well, it's not very evident here, but as you will see, that this shared memory is going to be much closer to your cores than the global memory. Right? So this global memory is our RAM, GPU RAM. So whatever data we did using CUDA malloc, all of that gets allocated in this global memory. And accessing it is going to require, let's say, some number of cycles, let's say 400 to 800 cycles, as we mentioned here. Okay. But the shared memory being a little closer to the GPU core, the access time is going to be better. Then why not put all the data in shared memory? Well, there are two reasons. One, shared memory is not accessible across all the threads on the GPU, unlike global memory. As you can see, global memory is universal across all the threads. So you write from one thread in a particular memory location, you'll be able to access it from the other thread at a later point in time. But as far as the shared memory part is concerned, which is faster, that is going to be accessible only inside a block. Right? So if you have a thread block having, let's say, 1024 threads, then all those threads you can have this, that one thread writes and the other thread accesses it. But as far as one thread from a thread block and another thread from another thread block are concerned, they cannot communicate via shared memory. For them to communicate, it has to go via the global memory. Right? So in this sense, you should think about the shared memory is actually like a cache shared across these set of cores on which your thread block is run. Right? So if you have 1024 threads inside a thread block, then all those 1024 threads will have access to this on-chip cache. Right? That is also called as a scratch pad memory. Right? Since that is limited, we may not be able to put all the data, right? So so one thing is that it is not accessible across all the threads. The second thing is that it's limited. So we cannot always accommodate all our data into shared memory. It's going to be very small. Like, I mean, think about it like a cache only. In fact, it is mapped to the L1 cache of this streaming multiprocessor. But think about it like a cache, and therefore it's going to be available in a very small, tiny amount, a few kilobytes of memory. So that is going to be one part which we would like to take advantage of if we want to parallelize our code further. The second or the third type of memory that is available is essentially registers, which is there similar to what we have on CPU. So there are registers which are available for all the cores, and these are going to be core specific registers, and you can use them as and when, I mean, the compiler essentially is going to generate code such that those registers are going to get used for your local variables, for keeping track of temporaries, for passing parameters, etc. across functions. So the registers, you don't have any control from the programming perspective, at least at the CUDA level. You do have control over it at the PTX assembly level, but not at the high level. But shared memory you do have control over, and that is what we will exploit as we go along. Okay? There is a question by Nitin, I'll take that up. If the command queue is cleared every time his kernel is called, then how come when 32 threads for the same kernel is called, their thread IDs can be random? Isn't this a contradiction to the first statement? So the command queue is not clear. The command queue is cleared one by one with respect to the commands that are inserted. So since it's a queue, you insert, let's say I want to do kernel 1. Right? After that, I want to do kernel 2. So it's not that when you are doing kernel, when you have inserted kernel 2 as the next task to be taken by the GPU, that it's going to empty the queue. It's just that it's going to make sure that K1 finishes and then K2 is launched. Right? When 32 threads for the same kernel is called, their thread IDs can be random. No, that doesn't happen, because if you are launching the next kernel, always the kernel thread IDs are going to be always from 0, 1, 2, 3, 4 like that. Right? As far as.
Hi, sir.
Yeah, sorry, go ahead.
Can you hear me?
Yeah, Nitin, go ahead.
So, sir, the reason I asked this question is in the first lecture, you were saying when you're demonstrating the fact that GPU synchronizes the function from CUDA, without which the CPU won't wait for the GPU to do its work and just continue asynchronously. But if we include that CUDA function, it will wait for the GPU to finish its work, right? And in that, you explain like if we call D kernel 3 times and put that line over there, it will wait for line by line. The first kernel, say hello world 1, hello world 2, hello world 3. So in that parlance, you explained that due to the command queue being cleared for every time the kernel is called, it will be like synchronously. Step 1, step 2, step 3 will be in that order. Similarly, let's just say if we have another dkernel type function, which does just multiplication, let's just say square. X is the input and it takes X star star 2 in Python, or say just n exponent power, right? Multiplied by the power of 2. If we call this on an array of 1 to 100 elements, we need to take the square of every 100 elements, or square of every element in the list or the array in C++, and just return that in place, right? So single function, the multiplier function or the fun function or whatever function we call it, it is going to be called 100 times, right? And if this is getting called, then obviously shouldn't the output by default be 1 square, 2 square, 3 square? But you explained that the output could be 1 square, 64 square, 17 square, right? It could be asynchronous. So that was my doubt, that if this can happen, then like, isn't this a contradiction for the command queue part? That was.
Sure, yeah, that's a valid doubt, Nitin. So it turns out that as far as 32 threads of the warp are concerned, they are always going to be in sync. So 0 to 31 threads, their output you will always see in order. Okay, but that means that if you are going from 0 square to 31 square, then you will always see this in the exact sequence as we have seen in the sequential setting. But 32 square to 63 square, this is going to be a different warp. Warp meaning a set of 32 threads. So since there is going to be a different warp, these two warps do not have any kind of synchronization by default. So it's possible that you might execute the first warp first and then the second warp, or the other way around. And therefore, but as far as 32 to 63 squares are concerned, those again are going to be in exact sequence. But these two blocks of squares might occur in two different ways. And that is the reason, and the same is true with respect to other warps also. And that is the reason why you can get that randomization across warps, but within a warp, the way it gets implemented, you will not see that randomization.
Okay, so you're basically saying, sir, that the groupings, basically they are grouped by now these 32, you could say, size chunks. So it could be that 33 square, 37 square, 63 square would come, but it won't be that 31 square, then 1 square, 2 square. That it won't.
Yes.
It would be among the group, their groups, respective groups itself.
That is correct. Yes.
And it always happens in 32. Is there any reason for that, sir?
No, it's just that that is what people have found out to be the, I mean, the architecture designers have found out to be the reasonable size based on the benchmarking that they have done and various applications that people use across the world. So that is the reason why that 32.
Okay.
It's possible that in future it might change to 64, but it's been more than 10 years that it is fixed at 32.
Okay. Thank you. Thank you. So it is by design then. Okay.
Yes, yes, it is by design. Okay. Tony is asking, is there a stack concept in GPU similar to CPU? Yes. In fact, there is a recursion also on GPU possible. The stack, unfortunately, is a little limited since there are large number of threads and each one needs its own stack. Therefore, there is a kind of limit which is going to be much lower compared to what you will have on a CPU. But yes, you can write recursive codes on the GPU. You can call a function from inside the kernel and you will be able to call it recursively also. So all that is definitely supported and all that is definitely required also. Okay. Okay. So please feel free to ask further questions in the chat or directly by unmuting. I will continue otherwise. So this global memory, which originally in the context of graphics processors, right, before graphics processing units, we used to have graphics processors. In that context, it used to be called as VDO memory or VDU memory. And that is the primary place where we keep all our data. This is like our DRAM on the CPU, so the access latency is going to be much higher. And the throughput that it gives is going to be reasonable, but it's not going to be as high as you would otherwise expect for a very parallel system. There are other two types of memories, and apart from shared memory, called as texture cache and constant cache, or texture memory and constant memory. These are read-only memories, which means that you can write to them once, and then during the kernel execution, you can only read them, you cannot modify. Because of this read-only nature, this can be cached nicely, and then there are no invalidations possible, and therefore the cache hit rate is going to be much better. Unfortunately, these memories are also very, very small, a few kilobytes of memory, and therefore these are not really useful to keep data. But these are very useful in some cases to keep some sort of metadata. Let's say about your computation, you want to keep some aggregate information, or you want to just pass a very small amount of information between CPU and GPU. Then these texture and cache memories can turn out to be very useful. We will be focusing more on the shared memory, which I will go to as the next part. Right. So there is an L1, L2, the similar cache hierarchy as on the CPU. Let's talk about the L2 cache first. This L2 cache is, let's say, close to 1 MB of cache, which is going to be shared across all the streaming multiprocessors. In the computation hierarchy, we had thread, then block of threads, multiple blocks of thread, then warp, then thread block. Multiple thread blocks are assigned to one SM, that is the streaming multiprocessor, and then multiple such streaming multiprocessors form the GPU. This streaming multiprocessor has this L2 cache, and therefore it is going to be shared across, it is at the GPU level, and therefore this is going to be shared across all the streaming multiprocessors. Very similar to what happens on the CPU. But unlike CPU, which is going to have a few tens of cores, the number of cores on the GPU is going to be a few thousand, and the number of threads with which you are launching it is going to be, let's say, a few tens of thousands. Therefore, the amount of cache that you have is going to get split across these threads. Right? Think about it this way: that as you, if you have fixed number of chocolates and you want, or a fixed amount of cake, and you want to distribute it amongst 4 people versus 40 people, then you are going to get a smaller chunk. Right? In a similar manner, you are going to get this smaller chunk of this L2 cache or L2 cake. Right? And therefore, it's possible that your memory related or caching related optimizations that you know and you did on the CPU might not give you enough benefits on the GPU. Right? And we'll see how to optimize that. And that is where the L1 and L2, L1 or shared cache or shared memory comes into picture. One last point about L2 cache is that since it is shared across all the threads on the GPU, you can have an atomic instruction go all the way up to only L2 and come back. That is, it need not go and update the memory on the DRAM, in the DRAM, right? So it need not have those many number of cycles. If there is L2 cache available and it's a write back mechanism, then it's possible that it might be able to improve the performance of your synchronization across threads. That synchronization is what I'm referring to as atomic instructions, right, which we will study when we deal with synchronization in our next class. Let's focus on this L1 and shared memory. Right? So each SM is going to have its own L1 cache. This L1 cache is configurable. Right? So CUDA architecture has made it configurable. So you can configure it as you can have 16 KB of shared memory and 48 KB of L1, or vice versa. It's also possible that you can configure it as 32 KB of shared and 32 KB of L1 and so on. But what does that mean? What that means is that when the cache is getting used for your threads automatically by the hardware, it will use this L1 part. And when we say that it is going to be a shared memory, this memory is left for the programmer to program. So you can decide what goes into this cache. As a programmer, you can decide that this data is more frequently accessed and therefore I want this to go into this particular memory location. So you are going to get an array or you can declare an array which is going to go into shared memory. So that is going to get cached and you can read as well as write to it, right? Unlike texture and constant memory. And therefore this becomes more appealing in several applications that have you exploited shared memory because that is required when you have a good amount of data and memory becomes a bottleneck. So like L1 cache, it has very low latency and it has definitely, because of that, it has a high bandwidth. That is the amount of data transfer that you can do per unit time is going to be much larger. I have talked about registers, so I'll skip that. Okay, there are no questions, so I'll move ahead. There are two concepts which are very important from when we deal with memory or rather communication. Right? So one of the concepts is bandwidth, the other one is called as latency. These two are related, but still we might want to focus on one in a particular architecture. For example, when we want to increase the bandwidth, we would like to have a wide data bus, right? A fat data bus or a big data bus, right? Rather than a lean fast data bus. That lean fast data bus means that it is going to be improving your latency, right? So think about it more like when you are running, this is like a sprint versus you are running a marathon, right? But if you want to run a marathon, you don't want to run alone. You want to have lots of people running with you. So this wide data bus is like a little marathon, which might be slow, but you are running with large number of people and therefore you can get the amount of work done might turn out to be larger, right? In this case, the data transfer, which is happening in parallel, might turn out to be much better per unit time compared to a fast data bus, which might be very fast, but because of the cost involved and technology involved, you might just have let's say one or few lines of this data bus, which is more important on the CPU, whereas the GPU people have decided that they will do a throughput based architecture rather than a latency based architecture, and therefore this data bus, the communication between CPU and GPU via this wide data bus turns out to be very important, and we should optimize our codes for improving this bandwidth. So how do you optimize those? Just a few ways in which that can be done is that one thing is you don't use too much of data. You don't transfer too much of data, rather. So if there is some array which you have used and you want to now make reuse of that, make that reuse so that the data transfer might turn out to be less, or the memory allocation related overheads get reduced, right? Memory allocation as well as deallocation. Data compression is another technique where you don't want to, I mean, since the data is much larger, but there is a lot of commonality in the data, so I want to do some sort of a data compression, which is likely to be, in most cases, going to be lossless, which means that you will be able to retrieve the data back. So you compress the data, let's say on the CPU or on the GPU, and transfer the data, which is going to be smaller than the original data. So that data transfer happens relatively faster, and then on the other device you uncompress the data and start working on it, right? So that is a nice way in which you can improve the bandwidth of your computation. In certain applications, especially the numerical computations, right? Especially the numerical computations that we observe in high performance computing, there are several applications which do not demand exactly the same amount of, say, exactly the same data. So you may be able to afford a little bit of approximation, which might allow you to compress further. You might not be able to get the exact data, but if you are worried about that, okay, as long as my error is 10 to the power minus 6 or 10 to the power minus 5, I'm okay with that, right? So therefore, those approximations might turn out to be useful when you do the data transfer. There is also a body of work which says that if there are small computations, you might just want to recompute it rather than transferring the data. So you have already computed the data some time back and you have transferred it to the other device. Now you want to get further again access to that. So instead of transferring it from the other device, you just recompute it on the same device. Then this might turn out to be useful in some situations where the computation is fast and the data transfer cost is too much. In such cases, it might be okay. Okay, let's come to the flip side of that, the latency. Latency means that you are running a sprint, you are running fast, right? You are not interested in running slow. But because of that, the technology and the cost of the line might turn out to be high. So this is the time required for performing the transfer or the I/O. When I'm talking about I/O, there are multiple meanings of this I/O. The I/O might be from CPU to memory. The I/O might be from CPU to GPU or GPU to CPU. So across devices or within a device. In this case, what we are talking about is across devices. Ideally, we would want latency to be zero. I mean, there should not be any latency. As soon as I want the data, it should be available. That is what I expect. But unfortunately, that doesn't happen in practice. And memory I/O can become a bottleneck. Right? So the I/O that we are talking about between CPU and GPU, that can become a bottleneck. In general, even CPU to memory or GPU, I mean the core to memory, this data transfer, which might involve multiple stages, caches, as well as if there is, the caches available at the streaming multiprocessor, as well as there might be a last level cache available across the GPU, and then the DRAM. So all of these stages, when the data is passing, that somewhere you might have a bottleneck depending upon how the data is organized, how the access pattern is, etc. So remember that it can become a bottleneck as soon as you get into more complicated programs, which are not really easily parallelizable. So therefore, we would like to improve the latency also. First things first, I mean, on CPU, we have this hierarchy from registers all the way to RAM. The latency increases and the cost per unit storage, as well as the amount of storage that you have, that goes on increasing, right? GPUs have very small amount of L1 and L2 caches and large number of threads. Therefore, the splitting of the cake turns out to be very small amounts, a very small piece comes to individual threads or individual cores. Therefore, there is a different way of attacking this problem of hiding the latency, right? So we want the latency to be ideally zero, but that doesn't always happen, but we would like to hide it as much as possible. So the way this gets affected is that on CPU is that you're executing certain instruction, let's say load instruction, and now you want some data to be loaded from DRAM. Assuming that it is not there in the intermediate caches, is going to check those and then load it from DRAM. Now this is going to take several hundreds of cycles. Now for several hundreds of cycles, the core cannot be sitting idle. Therefore, it needs some other instruction to be executed. If you have multi-threaded program, you can possibly take another thread. But if it's a sequential program, maybe there is another instruction which is not dependent on this instruction which you might be able to execute. But then how many such instructions you will have to really execute? And therefore, this problem of identifying so-called independent instructions or instruction level parallelism might turn out to be a challenge if you have large number of memory IO operations, and therefore if the data is not available, there is no further instruction to be executed by the CPU, then CPU doesn't have any other choice but to halt, right? Despite having all of these branch prediction, etc., algorithms kicked in. So, so that is the reason why I would like to hide this latency. If it's possible that there is always some work for the CPU to do, then you can actually remove whole latency, because the CPU or the core is always busy. In a similar manner, on the GPU, the same thing happens. That the core is executing an instruction, when it wants the data may not be available, and therefore core does not have anything to execute. So what it can do, since we are talking about a parallel GPU architecture, is that instead of waiting, it can, of course, take up another instruction which is independent of this instruction. But what if it exhausts all the instructions, parallel instructions? In such cases, it might be helpful that maybe some other thread which is free to execute, which has the data available, maybe the core can start executing that. And why this turns out to be useful, especially in the context of GPUs, is because you have a very large number of threads with which you are launching the kernel for reasonably sized applications. And therefore, you almost always have some threads which you will be able to execute on the idle cores. And therefore, this is the concept of that I exploit massive multi-threading, that is the large number of threads, to actually hide the latency. So when the one particular thread or one particular warp is waiting for the memory to be available, I'm going to execute another warp, right? I meaning as a core or a set of cores. If that also halts, then I'm going to execute another warp and then another warp and another warp, right? How many warps do I have inside a thread block? Assuming that you have 1024 threads, how many warps do I have inside a thread block?
Well, 32.
Right. So it's going to be 32, right? The 1024 divided by size of the warp, which is going to be 32. So we have so many warps in one thread block itself. And therefore, there is enough time for the GPU to execute these warps. And by the time the last warp executes, it's possible that the first warp, which was halted, by then the data is possibly going to be available. It's also possible that the stalling can still happen. Right? It's not that the latency is going to be fully always removed in the context of GPU. Whatever is possible on the CPU, the same thing is going to be applicable on the GPU also. But the architecture is designed in such a way that you would like to hide this latency by taking advantage of this massive multi-thread. Okay, good. So, so these are the two aspects that we would like to keep in mind: the latency and the throughput. And GPUs are throughput-oriented architectures. So, pictorially, I will show how this happens and exactly the way we just discussed. But it might be helpful to see it as a visualization. So, y-axis downwards, I'm going to show the time, and then there are different steps, time steps that I'm showing. Let's say there is a thread block which has multiple warps, which is executing. And then when it starts executing, it's going to execute for some time, and then there is a stop. Right? What does that mean? That means that the data is not available, and therefore it is going to not execute any instruction. But at this stage, I can take those free cores or that free streaming multiprocessor or those, essentially the hardware elements, and then take another warp and start executing that, because that is scheduled or that is free to execute. That might also reach a stall, and so on. And similarly, you can have multiple such warps being executed or multiple such thread blocks being executed. At some point in time, when this stall is over for the first thread block, at that time I can start executing that particular thread. Right? So I hope this pictorially it shows how this is going to be helpful. And if you do this pipeline little carefully, you will be able to see that you might be able to almost remove the latency hiding if you are lucky in this business, right? So after this particular stall is over, this particular execution is also over, and therefore you might be able to execute this particular block here also, and so on. Right? And that way the latency is hidden. How do you know that the latency is hidden? Because at every time step, the cores have some work to do, useful work to do. If that is the case, then there is no stall. And therefore there is 100% utilization of this particular hardware element, which may not be useful from energy perspective. That is a different ball game altogether. But from the execution perspective, this is going to be useful. Okay. It's also possible that in some cases you might see, because of this, that when you are running it with a single thread block, or running it with a single warp, or running it with a single thread, you might see some performance, and when you run it with more number of them, you might get into super linear speedup. That is, when you increase it by n number of hardware elements, you might get a speedup which is more than n, right, compared to the original execution with the stall. And that happens, as you can see, you can just do some calculation. This is similar to what happens in pipelining, where you can get a linear speedup, a super linear speedup in the when there is a caching is in effect. Right? Exactly in a similar manner, you will get you can get super linear speedups here also. But keeping that aside, you can definitely improve the latency, and therefore the overall execution time is going to be much better. Whatever I have shown just now, that automatically happens, and you don't have to do specifically, explicitly anything with respect to your code. However, it's important to know this concept. The reason being that sometimes you might want to remodel your computation to suit this. Okay? So that we'll study when we study a little bit of synchronization. But anyway, just keep this in mind that this is happening in the background. Okay. So when we are dealing with memory, we know that the locality is very important. And what are the two kinds of localities we know of in the context of CPU? Spatial is one, as Elakia has said, and then Harish says spatial and temporal. Right? So these are the two main localities that we talk about. Right? Can somebody tell me what is spatial? And somebody else can tell me what is temporal. Like array, spatial, yes, correct. So whenever I am accessing a particular memory location, let's say A of I, it's likely that I am also going to access nearby memory locations. Let's say A of I plus K, right? In general I plus 1, I plus 2, like that. So that is called as spatial. And temporal means? Harish says a loop statement for temporal. Right. So whenever I am accessing a particular memory location, maybe I am going to access the same memory location after some time. Right? That is called as temporal, in time and in space. Right? So those two are also applicable in the context of GPUs. Right? So all threads in a thread block have this L1 cache, which is going to be essentially doing exactly the same processing. So locality is going to be important. Right? This we discussed earlier. And we should try to exploit this as much as possible. However, in GPU setting, a little bit of difference comes into picture when we are dealing with warps, and that is the reason a slightly different form of spatial locality becomes rather critical. Right? So there are these two words are very important. Locality is important, and another form of spatial locality is critical, and that is, I have used this very carefully. The reason being that your performance is affected by the temporal and spatial locality, definitely, but it is affected lesser than what it is going to get affected with what we are going to discuss now. Right? So let's get into that second part of locality. Right? So I'll just recap our spatial and temporal. Spatial means A of I is accessed, so A of I plus K is also accessed, and A of I is accessed now, it will be accessed soon again. Right? So for example, if I have such an access pattern where I is increasing, then there is a spatial access pattern. Whereas if I'm accessing, let's say A of I, then I'm again reading A of I and then again reading A of I. There is a temporal access pattern for A of I. Yeah, these are little more applicable on the CPUs. Let's come to what happens on the GPUs. Well, I'll skip this classwork. I'll leave this for your exercise. But essentially what this is doing is that you have matrix multiplication, C of ij plus equal to A of ik into B of kj. And the loops are ijk in that order. You might want to just change that to ikj, keeping this access pattern the same, and see if you get any performance benefit. These are sequential CPU code. Okay, you can run it on the CPU and just see if you get any performance difference just because of interchanging of the loops, and we can discuss that if required. Okay. In fact, I got a difference, so you can check what happens on the GPU. We have already done the matrix squaring program on the GPU, so you might want to try by interchanging the loops what happens. But let's come to the locality that we are talking about in the context of GPUs. So the locality is because of a phenomenon on GPU which is called as memory coalescing. So what is memory coalescing? Memory coalescing says that, let's read this first and then we'll try to understand. If warp threads access the words from the same block of 32 words, their memory requests are going to get clubbed into one. Right? What this means is that if consecutive threads of the warp, let's say 0 to 31 or 32 to 63, or if all of them access A of thread ID x.x, right, then they are going to access consecutive memory locations. Then instead of making 32 rounds of this memory accesses because you want the data to be brought in or returned to, those are going to get clubbed into one memory cycle by the hardware. That is called as coalescing the memory accesses of a warp. This concept is applicable only for the warp and not for two threads across warps. Okay. This can turn out to be very important because that also deals with how our access pattern is. Typically, the way I am going to write my programs, if it is going to be A of thread ID x.x, then I already have coalesced accesses. But if it is not like that, then I need to be a little more careful. Okay, and we'll get into some of the examples now. So if you do not have the coalescing, then each load store can require one memory cycle. And this memory cycle is going all the way possibly to DRAM. If the data is available in between, it's good. But it can potentially go to the DRAM, and it can require 32 memory cycles. So 32 into 400 kind of CPU cycles, this can be the worst possible time that you can require to get your data. When can you have this access pattern such that you have very, you don't have coalesced accesses? Can somebody think of an access pattern which is fully uncoalesced? Okay, I don't see any responses. Okay, so one thing is, of course, that random access pattern, right? Instead of saying A of thread ID x.x, I am saying A of some random function of thread ID x.x, in which case I might get totally arbitrary indices across warp threads. That is one. The second thing, so the random access pattern is not so common unless you are just trying something. But the second aspect which comes in where this access pattern is not so regular is when you have data dependent access pattern. This data dependent access pattern occurs in the context of something called as irregular codes, and graph algorithms or sparse matrix computations link you to these arbitrary accesses. And in such cases, coalescing turns out to be a very important optimization to improve processing time. Yuraj is asking a question: does coalescing be handled by the CUDA programming internally, or should we have to manually handle this in our program? It is going to be dependent on our access pattern, right? So how am I accessing the array? That is going to be dependent on me. How I have structured my data, that is going to be dependent on me. Once I have it in consecutive threads are accessing consecutive words, then the hardware will do it automatically coalesced. Okay. Uh, okay. So yeah, this can considerably reduce the throughput, and therefore, in such cases, only the compute-heavy kernels will be really useful. So we would like to avoid that. I mean, you would want that it should be useful even if you have memory-hungry programs. Right? So that is where the coalescing part comes into picture. So for regular code like dense matrix computations or the usual array index operations, it is automatically coalesced, right? I will show you pictorially how it looks like. Right? So different consecutive threads. Okay, I am running out of battery, so let me just bring my chargers. Just give me 1 minute. I'll be back. All right, sorry about that. I forgot to get my charger. All right, so in this particular picture, we see that consecutive threads. So assume that these are all warp threads. In this case, let's say 8. So for all these 8 warp threads, if they are accessing consecutive memory locations or consecutive words in the memory, then the access pattern is fully coalesced. And therefore, they are just going to require one memory cycle to either fetch the data, load, or store the data. Okay? The uncoalesced access pattern will look something like this, where you are accessing arbitrary elements of the array. This is uncoalesced. Can somebody tell me how this access pattern is?
Random.
Random. What? Any other suggestions? Tony says maybe data dependent. Sure, that is correct. So now the question is for this random or data dependent pattern, whether it is going to be coalesced or not, whether the hardware is going to convert this into a coalesced access or uncoalesced access. Right? So Harish says it is going to be semi-coalesced because some part seems to be coalesced, some part may not be coalesced. Right? Any other suggestions? Rahul says coalesced as all the accesses are in that locality. Okay. So we have only one remaining answer now. Rahul says not sure if hardware will be able to figure it out. Yes, that is important. So it turns out that the hardware is able to figure it out. Right? And therefore, the last access that I showed is actually going to lead to a coalesced access. So the hardware doesn't care which thread is accessing what memory location. As long as these are coming from the same block of 32 words, it's going to be coalesced. Okay? So that's a good thing. Of course, it's very difficult to get this particular access pattern, but this is primarily for our own understanding. Right? If there are any questions, feel free to ask. Okay, so let's come to this question that Yuvraj's question, that is it going to be my kind of responsibility or will the hardware take care of it? It's going to be almost always my responsibility, but I need to know what the hardware is doing. Hardware is going to help us, but we have to put it in a way such that the hardware is able to take advantage of this coalescing. So for example, if I have A of thread ID as the access pattern, then it is going to get coalesced, right? So having this A of A is an array, ID is the thread ID, either thread ID x.x or the global ID, right? Which is the block ID x.x into block dim.x plus thread ID x.x, either way. As long as consecutive warp threads are accessing this in this particular manner, it is going to give you coalesced access. For this, I need to have the data stored in this form such that consecutive threads can access consecutive data elements. Okay, that depends. Sorry. Um, although the random case doesn't come, what can come is a strided pattern, which is quite common in our access when we access arrays. That I might have a thread accessing multiple elements of a chunk, right? So one thread is accessing consecutive elements of a chunk. Okay, so in that case, that is going to be the case that the chunk size, if that is either pre-decided or decided based on the amount of data, then there is start I can compute based on the thread ID, and then there is end, which is going to be start plus chunk size, and then I'm going to go from start to end. Your access pattern is A of II, which is definitely dependent on the ID, thread ID, but it is not that the consecutive threads are accessing consecutive words. It's just that one thread is going to access the complete chunk of data, another thread is going to access next chunk and so on. This strided pattern where this can lead to uncoalesced memory accesses. Okay. So can somebody tell me what should be the stride to get fully uncoalesced memory access? I'll repeat the question. What should be the stride to get fully uncoalesced memory access? Tony says 32 blocks. Any other suggestions?
We don't use ID.
We don't use ID, that is correct, but this II is actually dependent on ID. So II depends comes from start depends upon ID. So there is a dependence on ID that is anyway going to be required. But it's just that the consecutive words are not always going to be accessed by consecutive threads. Right? So we'll take Tony's suggestion. Yes, whenever the stride is 32, it's going to be fully uncoalesced. And when will you have the fully coalesced access? Elakia says increase the chunk size. Yes, correct. So we increase it, and as you increase it from 2 to 4 to 8 to 16 to 32, the coalescing goes on reducing, and at stride equal to 32, it is going to be fully uncoalesced access. For stride equal to 1, it is going to be fully coalesced access. What is meant by stride equal to 1? Stride equal to 1 in our case means that consecutive threads are going to access consecutive words, right? So the words that are going to be accessed by consecutive threads are separated by 1 or the stride length access, and therefore stride equal to 1 means that it is fully coalesced. So this stride can actually give you a good kind of tuner or a tuning parameter to change the amount of coalescing that you can get, and you can check the performance whether it reduces from fully coalesced k equal to 1 or stride equal to 1 to fully uncoalesced k equal to 32. Okay, sounds good. If you have such an access pattern, which is not uncommon on the CPU, by the way, even on the GPU many times we use this, you might be able to reconvert it or rewrite it such that it gets a fully coalesced access. Can somebody tell me how you will do it? So you are having this uncoalesced access pattern and you want to make it fully coalesced. What will you do? Meanwhile, I will take Rahul's question. Is word size same as size of int? Yes. We are taking word size as size of int.
Mod of 32.
What of 32, Yuraj?
Mod of 32.
Mod 32. Okay, so that will be what? Mod 32 will be what?
1.
Okay, I think I didn't hear it properly.
Instead of going start to end, we split the entire loop into mod of 32 so that each chunk will be executed. So that
limited number of threads.
Limited number of threads.
Okay. Okay, that was a good plan. Okay, any other suggestions? Thanks, Yuvraj. Okay, so what we are currently doing is that we have large number of threads and the amount of data is much larger, right? Let's say 4 times, 8 times, something like that. So what we are saying is that if it is 4 times larger, the data compared to the number of threads, then give each thread 4 consecutive words, right? Instead of that, what we could do is that take the number of threads and give them consecutive IDs. And then take the same set of threads and give them next consecutive IDs of the data, and then next, and then next. So the stride is still going to be 1, and you are going to process just the data. But now, when you go for the next iteration of the thread, you don't go by the chunk size, you go by the number of threads. And then one thread is going to access, let's say, 0th element, then 0 plus n, 0 plus 2n, and 0 plus 3n, where n is the number of threads with which you are launching the kernel. And that is going to give you a fully coalesced access every time, right? So this pattern is very important. And if you have such a pattern, strided pattern in your codes, you should convert it to have coalesced pattern. Okay. All right. The random pattern can be either coming as totally random value, or it could be input dependent, or that is also called as data dependent. Right? So when you have A of input of like that nested array index, that is going to give you very uncoalesced access. There won't be any guarantee in terms of coalesced accesses. All right. So on the CPU, let's summarize this. On the CPU, each thread should access consecutive elements of a chunk, right? So this kind of consecutive elements being accessed. This pattern is going to give you better spatial locality. This access pattern will give you better spatial locality, and therefore you should have this particular, all the fields of the structure should be together, and that is what we do, right? So when we declare our structures on the CPU, we say that all the fields related to a particular record are going to be declared together. I have an array of these structures, and that is going to be my data structure. So that array of structures is going to give you better locality, because the hope is that whenever I am accessing that array of I dot field 1, I am going to also access field 2. Right? So that is the hope. And therefore, spatial locality turns out to be useful when you have array of structures. In contrast, on the GPU, we say that the chunk should be accessed by consecutive threads, right? And that means that I should not have field 1 and field 2 together of the structure. I should have field 1 of I followed by field 1 of I plus 1. I should not have field 1 of I followed by field 2 of I. I should have field 1 of I and then field 1 itself of I plus 1, then I plus 2, then I plus 3. All of these put together, and then I should have field 2 of I, then field 2 of I plus 1, field 2 of I plus 2, like that. Right? This pattern of storing your information is called as the opposite structure of arrays. So you essentially have an array which contains all fields 1, all field 1, all field 2, all field 3, and then you put all of these together, which is called as a structure of array. So you will see these terms quite often in GPU related nomenclature, AOS versus SOA optimization. Right? So AOS is array of structures which has this strided access pattern, spatial locality on the CPU, whereas structure of arrays is essentially going to get you to coalesced memory accesses. Okay. How do you declare those? Well, in the context of CPU, we have these different fields put together, and then we have a structure of all these nodes, so that what we expect is that when a thread is accessing one attribute, one field, it also accesses other fields of the same structure. Okay. In contrast, we should have on the CPU all the A fields, all the B fields, all the C fields together as consecutive elements, and that gives you an array of each of these fields. and then you put all of these together inside a structure, so it becomes a structure of arrays, right? And the expectation is that whenever a thread is accessing an attribute of a node, a field of a node, its neighboring thread I plus 1 is going to access the same field of the next node, right? Whenever I am accessing a of thread id x dot x, my thread id x dot x plus 1th thread is going to access a of thread id x dot x plus 1, right? That is the hope. That is the expectation, which leads to better coalescing. Okay? Any questions on this coalescing part and what happens between CPU and GPU and why we need to have a little different form of locality? It's still locality. It's slightly different form because of the way warp threads are working together. All right, I don't see any questions, so I'll move ahead. Can you write code for the two types using CUDA memcopy? So all arrays will get converted into pointers because you want to move it to the GPU. But in the interest of time, I'm going to show you the code. So in the context of array of structures, that is on the similar to CPU side, I'm going to have a pointer to the structure all nodes AOS, and on the GPU I'm going to have individual arrays allocated, right? And therefore I'll have these 3 pointers inside the structure. So the way I'm going to access it in the GPU, right? So both of these are on the GPU. It's just that, I mean, you can have AOS on the GPU also and SOA on the CPU also, but the performance is the only thing that is going to change here, depending upon the access pattern. So I'm going to access .id, sorry, .a, .b, .c, all of these together in the array of structures, similar to what happens on the CPU, and this will have fewer coalesced accesses because A of id plus 1 is going to be now strided by whatever is the number of fields. Okay? So therefore, this becomes a strided access, and as it goes on increasing, which means that the structure size increases, the stride goes on increasing. In contrast, we are going to have A of id, B of id, and then C of id. So all the warp threads are going to execute this completely first. Then all the warp threads will execute B of id, and then all the warp threads will execute C of id. Therefore, at every stage, you will get coalesced accesses in the green case, SOA case, whereas in AOS you will not have that. Right? Any question? This is an important part. And once again, I will say that you can write, this code is written on the GPU, so you can write this code, and that is how you will transfer, because on CPU, typically when we port our code from CPU to GPU, on CPU you have this structure, so you create the structure on the GPU and you get lesser performance, and you should know how you get less performance, and therefore you need to remodel your data, not only computation, remodel your data such that it follows the SOA style. As I'm showing you, AOS style, exactly the same amount of data, there could be a huge difference when it comes to the amount of time that it takes. Okay, so this is one important piece. This classwork I will leave to you. You can try copying a linked list from CPU to GPU. You will get into a lot of issues. Not that GPUs are really used for linked lists, right? So that is not really the case. But this is going to help you in understanding where you get into issues, right? And if there is any question in this, feel free to post on the group and we can discuss. Yeah. So the second important part when we are dealing with GPU memory is our shared memory. Let's come to that part. So it's a programmable scratchpad memory which is accessible to all the threads inside a thread block. So all 1024 threads, 768 threads, 512 threads, all of them will have access to this shared memory. The way I'm going to declare it is that I'm going to just mark a particular variable as underscore underscore shared underscore underscore inside the kernel. Inside the underscore underscore global underscore underscore kernel, I'm going to mark some variable as shared, and that just is going to push that variable as accessible across all the threads inside shared memory. Okay. To that, I can do A of id equal to id, where id is the thread id, and since I have declared it of size n, that means that all the threads of the thread block are going to access different memory locations of this array A. And it also means that if I write from one thread, the other thread will have access to it within a thread. In a similar manner, I can declare a single scalar variable s, and I can say that if my id is 0, then s equals 1. Okay. The question now is, what should this id be? So what is this ID that I'm talking about? Any suggestions?
Thread ID.
Okay, why is that?
Because this shared memory is accessible only inside the block, so it should be 1 to 32. Yeah.
Okay. So as Yuvraj has rightly pointed out, this memory is accessible only within a thread block. So if you are accessing it with a global ID, block IDX into thread ID, block dim.x plus thread ID, that means you are doing something wrong, right? By and large. Right? This is the pattern that you will see, that if you are using shared memory, the access pattern should be with thread IDX.x, local ID, not global ID. Okay? Because for different thread blocks, there will be different shared memory. This array is going to get repeated number of thread blocks number of times. So there are number of thread blocks, many A of n's available, right? So if I did not have this shared, then the number of arrays is going to be equal to total number of threads on the GPU. Okay? With shared, the number reduces to number of thread blocks, right? Okay. So let's do a simple classwork. So what we do is that you are given a large integer matrix, and a row is assigned to a thread block. So ith row is assigned to ith thread block. Okay, which means that each thread block is processing one complete row of the matrix. And then each thread is assigned one element of this matrix. So each thread is essentially going to operate on m of ij. So that I becomes block idx.x, j becomes thread idx.x. Okay. Now what I want to do is to change this m of ij to m of ij plus m of ij plus 1 whenever possible. Right? So please understand what this means by wherever possible, and we would like to exploit shared memory in this particular classwork. So I request you to try it out, and if there are any questions, please feel free to ask. Okay, so as far as the last thread of a thread block is concerned, let's say 1024 threads are there inside the thread block, thread ID 1023 should not execute this code. Right? So we should say that if thread ID is less than block dim.x -1, then only execute this, right? So that is what is the first step. What is the other part that is going to come into picture here? Okay, so the other part that is going to come into picture is that there is a race. Race meaning that I am going to write to a memory location and also read from the same memory location at the same time. Because when a thread is writing to m of ij, it is going to read m of ij plus 1, which is also being written by the next thread. And therefore, that next memory location m of ij plus 1 is going to be written as well as read, written to as well as read from by two different threads simultaneously, and therefore there is a possibility of a data race. You might, yeah. So what is meant by a data race? Data race has, let's say, 4 conditions. One is there should be multiple parties, which means at least 2 threads. There should be common memory location. There should be at least one write, and there should be concurrent execution of these threads. Right? Only in such cases we say that there is a possibility of a data race. So in this case, since all these four are satisfiable, therefore there is a possibility of a data race, right? So that is one part. The other part, which is more relevant in the current discussion, is about exploiting shared memory. We said that shared memory is like a cache. There is no point in bringing something to the cache which is not going to get used often. So if there is something which you want to, let's say, access once, from DRAM you bring it to the cache, and from cache you bring it to the registers and you are accessing. There is no real reason to put it into the cache. Only if you are going to access it, let's say twice or more number of times, then there is the advantage of using cache. In this particular case, whether there is a reuse, that we need to worry about, right? So only if there is a reuse, then it makes sense to use shared memory. If there is no reuse, then there is no point in reading it. So this data race that I was talking about, you could get rid of that by splitting M of M as the input and another M as the output. So you separate the read and the write in time, and therefore you will be able to get rid of the data race. So you might have to create a copy. That is one way. There is also other way which we'll come to when we deal with synchronization. Okay. So let's see if you are able to understand this code. Right. So we have block size as 1024, and then there is a kernel. Right. And I'm marking this S as a scalar variable as shared. And then I have some assignments being done to S based on the thread ID. Okay. And I'm calling it with a single thread block. What you have to tell me is what will be the output of this program. I'll wait for a few seconds.
Random numbers.
It will print random numbers. Why is that?
Because everything is asynchronous.
Everything is asynchronous. Okay. Sure. Sandeep says it will print 2. Okay. Any other suggestions?
Oh, there is only one print statement, so it will print only 0.
It will print only 0. Okay. Hari says 1. Okay, so we have a good mix of answers, right? So it can print 0, it can print 1, it can print 2. Anybody wants to say it will print 3? Because we have s equal to 0, s plus equal to 1, s plus equal to 2. Otherwise, somebody will say we print 3 also. Shiva Krishna says same variable s is accessed multiple times, so race condition might occur. Sure. Okay, let's understand what is happening in this code. When we declare a variable as shared, that means that it is accessible from all the threads in the thread block, and in this case there is a single thread block, so we don't have to worry about it. Right? 1024 threads, this S is going to be shared. When we are accessing thread 0, S equal to 0 happens. Right? At this stage, okay, so I should also mention that since the size is 1024, there are 32 warps which are executed. Right? Now, only one thread of this whole thread block is going to execute s equal to 0 at some point in time. Is it guaranteed that at this stage, the other warps are waiting for s equal to 0 to happen? So we'll assume that this is going to contain some garbage, right? Initially, which is actually the case. So s equal to 0 when it happens, is it guaranteed that it will always be executed first before, let's say, s plus equal to 1 happens, or s plus equal to 2 happens, or when this printf is occurring? Any suggestions on that? Okay, So the Sandeep says CUDA synchronized. CUDA synchronized meaning CUDA device synchronized. Is that what you are talking about, or something else? Tony says, can thread 0 and 1 run at the same time? Sandeep says, yes, CUDA device synchronized. CUDA device synchronized is at the end on the CPU. It will not affect any of these. Only after all of this gets done, then only CUDA device synchronized will be reached. Okay, so can 0 and 1 run at the same time? Yes. In fact, 0 and 1 will run at the same time. In fact, on the GPU, we have this single instruction multiple data format where all the warp threads, that means all the 32 threads of the warp, will always execute exactly the same instruction, or some of them will probably be masked out. That is, they will not be executing any instruction. But it will never happen that they are executing two different instructions. Okay? Because, so this is called as SIMD processing. So let's understand in that context. But when s equal to 0 happens, that means that all 0 to 31 threads have to be finished, have to finish execution of this particular, this particular statement before any thread between 0 and 31 executes the second one. That is the SIMD style of processing. Hari says output depends on if warp containing thread 100 executes before warp containing thread 1. Sure. We'll discuss this. So therefore s plus equal to 1 cannot happen before s equal to 0 has happened. That is guaranteed because 0 and 1 are part of the same warp. So therefore they have to execute in SIMD fashion. As far as thread 100 is concerned, that is not part of the same warp, and therefore there is no control over whether it is going to get executed at the same time or later or earlier. Therefore s plus equal to 2 might read the value of s as garbage. It can read the value of s as 0. It can also read the value of s as 1. Okay. Therefore all these three can get incremented by 2 by thread number 100. When can thread 0 print? Right? Is it possible that it prints before thread 100 performs this s plus equal to 2? Yes, that is possible. But printf cannot happen before both of these get executed because they are part of the same warp. Thread 0 is going to execute s equal to 0. Thread 1 of the same warp is going to execute s plus equal to 1. Without these two statements, printf cannot happen. Okay? But it's possible that printf might happen before s plus equal to 2 or after s plus equal to 2 or in parallel to that. Alright? And therefore the number of values that you might see might turn out to be different if you run this repeatedly large number of times. Okay? I somehow got s equal to 3, but that doesn't mean that it will always give s equal to 3. Sometimes whatever is possible theoretically might not, you may never reach it because of a certain style in implementation, but we should always think also theoretically that other behaviors are also possible. Okay? So remember that you can print garbage here, you cannot print 0 here, right? I mean, unless 0 is a garbage, right? So this particular 0 cannot be printed in this because s plus equal to 1 is going to be intervening between s equal to 0 and printf s. Right? That should be remembered. Okay? Any questions on this? Feel free to ask. Okay. So now what I'm going to do is to change this a little bit. That little bit is right here. I'm just going to increase the number of thread blocks. Now can you tell me what all can happen? What is the change that is going to happen now? Any suggestions?
Two numbers will be printed.
Sure, yes. So two numbers are going to get printed because of two thread blocks. That is correct. Any other change that you see? Or there is no change that is going to happen? Okay, so interestingly, okay, no changes because shared memory is internal to one thread block. Yes, so that is correct. That you should have confidence that since these are two independent thread blocks, they are going to have two different copies of this S, and therefore whatever was the behavior for one thread block, that is going to be totally independent of the other thread block. So you will just repeat the behavior, but you will not change the behavior. Okay. Now if I run it in a loop, right, I might start seeing a slightly different. So you need to run it a few number of times. The code remains the same, but those of you who are careful readers will see this particular behavior, right? So that is what we were discussing just now. You might see different behaviors. So don't just rely on, okay, I ran it once, I ran it twice, I ran it thrice, and I got exactly the same answer. Therefore, my code is deterministic. Not necessary. Right? You have to prove it. Okay, so when we are dealing with thread blocks, right, all the threads, 1024 threads or large number of threads in a thread block, we said that there are two aspects to thread blocks. One is this shared memory, which we just discussed, which is fast access. The second one is a fast barrier between them. What is a barrier? Barrier is a point in the program such that every thread in the block is guaranteed to reach there without any thread going further. That is, if there is S1, so some statement S1, then there is a barrier, then some statement S2. No thread of the block is going to execute S2 before all the threads have finished execution of S1. That is called as a barrier. Right? So all the threads must meet at the barrier before any of them go further. Right? So think about it this way, that you are going from, let's say, Delhi to Chennai and you are passing via Nagpur, and you are deciding that you are going to meet at Nagpur, stay there, roam around, and then all of you are going to board the train for going to Chennai. So then Nagpur becomes your barrier. You are going to make sure that all of you meet there before any of you start your journey. Your journey might be independent of each other. You might take different trains, right? The journeys from Delhi to Nagpur as well as Nagpur to Chennai. But as far as the execution is concerned, you are guaranteed to be, all of you be there at one point in time in Nagpur, right? So that is what is a barrier. This barrier is called, is termed as __ sync threads, like a function inside your GPU code. And that guarantees that all the warps or all the threads in the thread block are going to finish execution of the previous. So like we had CUDA device synchronize for CPU to wait, this sync threads is going to be for all the threads of the thread block. Okay. So now if I put this, now can you tell me if there is any change in behavior with respect to the outputs possible? Okay, I don't see any suggestions here. Okay, there are some suggestions. Tony says guaranteed to be 3, CUSA is equal to 0 is printed. Okay. Yuvraj, you want us to say something?
Only 3 will be printed.
Only 3 will be printed. Okay. We have more votes for 3. Any other suggestions? Okay. So let's understand what is happening. We said that another warp, when thread 0 is executing S equal to 0, another warp might have gone ahead in the previous case when we did not have sync threads. And it might end up executing S plus equal to 2. Now it is not going to happen. They all are going to wait here. Okay. Only when all the warp threads, all the thread block threads, 1024 threads, finish execution of S equal to 0 statement, I mean, only one thread is going to execute it, but they are all waiting. Then only they all move ahead and reach this statement. The condition is evaluated by all the 1024 threads, but thread 1 only evaluates it to true and therefore starts executing S plus equal to 1. At this stage, the remaining 1023 threads can potentially go ahead, But as far as warp 1 is concerned, sorry, warp 0 is concerned, that is 0 to 31 threads, they cannot move ahead because of the SIMD style of execution. But threads 32 to 1023 will go and wait at sync threads. So thread 1 is going to essentially execute this statement while all other threads are waiting. Then all the threads come here and execute this condition. Only thread 100 evaluates it to true and therefore increments it to this, and all the other threads wait here. And finally, some threads might just finish execution, while thread 0 and warp 0, it prints the value of S, therefore it is guaranteed that the value is going to be all threes this time. Shiva, is it okay? Any questions on this? Sure. All right. And as you can see, this particular sync thread is actually redundant because it's anyway between the warp threads, right? So thread ID equal to 0, thread ID equal to 1. But anyway, sync threads is actually a very fast primitive in the GPU code, and therefore you can liberally put it at arbitrary number of places. If you are in doubt, just put sync threads. That's not going to hurt your performance, right? As long as you have more things to worry about like memory and synchronization. All right. So can somebody tell me what will be the output of this particular? Maybe I think it will be a little difficult, but it's going to be some sort of a permutation of ABCDs based on the block ID. So you can try this code out offline, but I have not specified block size, right? So if block size is not specified, then it's possible that it could be larger than 32, and therefore whatever I am writing to here, and if I am reading something here, right? Printf is reading str, so there might be a data race between the two, and therefore that is the bug in this program. And I would like to avoid that. Essentially, there should be a sync threads which separate this read and write, which will avoid this race. Okay. So this race between this write and read gets avoided because of this sync threads that you can check, and also check the output. Meanwhile, I'll take Harish's question. What would happen if multiple threads attempt to write to a shared memory location in a single class cycle? Exactly the same thing is possible. There might be a race. Now, by the way, I'll also mention one more thing. If the element that you are writing to happens to be a primitive type, like integer, then the hardware is going to kind of guarantee that out of all the writes, at least one of the write you will see. So that is called as concurrent read, concurrent write support. If that is given, which is there in our GPUs, then it is guaranteed that if multiple threads are writing, the output will be one of them. If the CRCW is not supported, then the hardware says that I don't guarantee anything. You can get a garbage value also, intermix of bits and so on. Yuvraj says thread deadlocks will not happen here. Not in this case, but in general it is possible. So can there be a deadlock if one thread is waiting for the other and another thread is waiting for the first? Can there be a deadlock? Yes. In almost all our parallel programs, deadlocks can occur, and therefore we should be careful while writing codes. So deadlocks can occur, but it will not occur because of this particular adding sync. Okay. All right. So yeah, so that is what I wanted to convey. There are certain functions which you can use, but I'll skip this part. That is more like a little more of detail. You can also specify dynamic shared memory, which, I mean, when we had declared the static shared memory, we had declared the parameter n. That needs to be a constant. But you can have arbitrarily sized shared memory, arbitrarily sized, subject to maximum memory possible, shared memory possible. So that can be specified as a third parameter of the kernel launch. But yeah, most probably you will not get into that because you can allocate the whole memory, 48 KB, that is available to you. So that is not really a problem. Only when that memory is stringent and you want to use it judiciously, at that time the dynamic shared memory comes into picture. So that I'll skip. Yeah, but I'll mention one small piece in the next couple of minutes and then I'll stop. There is a notion of banks, right? So shared memory, specifically shared memory. I'm not talking about global memory or other texture cache, etc. Shared memory is organized into 32 banks, and the accesses to one bank get sequentialized. And thankfully, the consecutive words are stored in adjacent banks, and therefore, if you have access pattern as threadidx.x, then you are all good. There is no sequentiality there. But if you do not have that access, then it's possible that if you are accessing the words from the same bank via two different threads, then the accesses might get sequentialized even if the two threads are independent. Okay, even if they are accessing two different words, right? So we should be a little careful about this. Bank conflicts is less of a concern in very synchronization heavy codes, but when you have very data parallel codes, at that time the bank conflicts can affect your performance. So you should be careful about that, especially in those situations. I'll give you one example. If I am accessing threadidx.x with stride equal to 1, that is not really a problem. But if I am accessing with a larger stride, then it's possible that there all the threads might be accessing different words from the same bank, and therefore you might get into this bank conflict. So we have to be a little careful when you have these access pattern, and you will not see the difference. I mean, compiler will not compiler will not say that you have bank conflicts in your code, and in fact the performance might just be normal, so to say. But if you remove bank conflict, then the performance can improve, especially for data parallel codes. So pictorially, if your access pattern is like this, then there is no bank conflict. These are all 32 banks, right? So you are accessing one particular word of a bank, and therefore it is all okay. If you are accessing multiple words of the bank from two different threads, then there is a possibility of a bank conflict, right? As what happens here. In this case, you are accessing arbitrary banks from different thread IDs, but there is no bank conflict because you are accessing single word from each bank, right? And you are accessing from different threads. So therefore, there is no bank conflict in this case. Yeah, so I'll probably ask you this quickly, and then you can tell me in which case you see bank conflict. First, second, third. Which cases have bank conflicts? Second and third. Harish says, Govind says third. Alekia says second and third. Okay, any other suggestions? Varun says none. Okay, interesting. Why, Varun?
Because it belongs, all the accessors are within the 32 word block.
No.
Because we are accessing the same bank, right?
And therefore there should be a bank conflict. If we are accessing the same bank, there should be a bank conflict.
But only if there are if we are accessing two different words within the
Exactly.
yeah.
Right. So that exception, which I didn't explain on the previous slide, Varun picked it up properly. That if there are threads which are accessing the same bank, but they are accessing the same word, then that is an exception that it is not a bank conflict. So actually, in none of these cases there is any bank conflict, right? So Varun is correct. I have those up now. Anything related to even the previous class related to computation path, thread, uh, uh, launch configuration, anything related to today's shared memory or bank conflicts or coalescing, feel free to ask. All right. So there are, I don't see any questions.
Professor, I had a question.
Yeah, go ahead.
Oh, I'm not sure whether this makes sense, but if you wanted to do some kind of matrix multiplication, and in that case, is it possible to put a row or column on a shared memory and do all the computation from other matrix and get a one row or one column of the answer? And is this a proper scenario in which you use a shared memory?
You can use it in this manner. That's a very good point. Thanks for asking, Raul. So you can put probably the complete row and probably the complete column, and you can get one cell of the resultant matrix. So can you use exploit shared memory here? Yes, this is a very good use case for that. There is a little generalization of this which is called as tiling, where instead of one complete row, you can possibly bring in one block of data from A, another block from B, and then you might be computing some partial sum of C, right? So that might turn out to be a generalization, but whatever you are saying, that is definitely possible, easier to implement also, which you should definitely exploit. Harish says, is it possible to give command line arguments in CUDA programs? Yeah, that is as in C. That is not a problem. Yes, you can. You can give parameters. So whatever we do in C, C++, all that is definitely possible in CUDA also.
So Harish, the way to think of it is a CUDA program is fundamentally a C++ program, and then some. It is an extension to C++ is how CUDA is envisioned. So since C++ takes argc-argv, CUDA can also take argc-argv.
Professor, another question about this, some of this optimization. Are there any profiling tools which would suggest us that because of this program, look at our static analysis and say, do this?
Yes, so there is a profiler called Insight from NVIDIA, which gives you information about some of these aspects. It will not advise you, though. Currently, it is restricted to that you can find out that this particular function or this particular kernel is taking this much time or this much memory percentage of time, etc. But it will not do an analysis of the program and say that, boss, maybe you can utilize maybe coalesced memory accesses, or maybe there is bank conflict possibility. That is currently not there. So that is why currently it is more like manual checking of your code and figuring out. There are a few research works which deal with this program analysis of the CUDA codes. Yeah, as prototypes, some of the codes might be available. I'll have to look it up. But yeah, those are going to be more like prototypes. These are not the kind of proprietary from NVIDIA or something. Okay, I don't see any further questions. Any other points, Pradeep, that we missed should be conveyed? Okay.
No, nothing from my side. Thanks.
Okay. All right, so we'll stop here. Your assignment 2 is already released, and we'll be, I think we have already made the code as well as private test cases for assignment 1 also accessible. So please run your codes on that. You'll be able to figure out where you made mistakes and learn from it. We'll follow a similar style for future assignments also. All right, I'll stop here. See you.